Good day, everyone. My name is Eirini Botsari and I'm the Community Manager of the OCCR, which stands for Open Science Community Rotterdam. OCCR welcomes academics and support staff working at Erasmus University and Erasmus Medical Center. We discuss, promote and adapt open and transparent scientific practices at every stage of the research cycle, from the initial idea to the final product. Most of you are acquainted with OCCR and some of you are members of this community. I would like to take this chance and thank you for your interest and support. In case someone that is not a member of our community and wants to become one, you can always email me and I will provide you with all the necessary information and instructions on how to join our growing community. I will attach my email address below in the description box. We organize journal clubs, talks on various topics related to open science, reproducibility and workshops. Today it's a workshop day and we are going to outline the key concepts of power analysis and provide you with a walkthrough of different types of power analysis using jamovi. Researchers have highlighted for decades that sample size justification through power analysis is the exception rather than the rule. Our wonderful guest speakers argue that one potential reason for omissions in power analysis is the lack of a truly accessible introduction. So may I present to you Dr. James Bartlett and Dr. Sarah.charles. James completed his PhD at Coventry University in England, and he is now a lecturer in psychology at the University of Glasgow. He is interested in developing educational resources on research methods and statistics. His background revolves around cognitive neuroscience and addictive behavior, and he is currently focusing mostly on research methods pedagogy. Our second speaker, Dr. Sarah.charles, completed her postdoc on the Cohen study at the Department of Psychology at King's College London. She completed her master's degree at Goldsmiths University and recently submitted her PhD in psychology at Coventry University in England. Her interests revolve around teenagers' mental health, the neurochemistry underlying specific mental health conditions, with an overall focus on social bonding. Similarly to James, her work involves research method practices and pedagogy. These two wonderful people have come together and wrote their article on jamovi, published as A Beginner's Tutorial to Power Analysis Using Jamovi. Thank you both for joining us today.
Everything.
To be fair, it's coming up with your signal being a bit shaky, so I think it's more down to your internet.
Okay. Right. Well, hopefully with James sharing his screen, but you're hearing my voice, it's okay. There is going to be a lot of me saying press next, please, James, because in general, for people who are hard of hearing, I like to put a lot of my things that I plan on saying at least visible on screen for the most part, so that anyone who is hard of hearing could at least get the idea of what's going on. But yes, so the main thing that we're going to be talking about 4 things today. I'm going to be taking over the first part and I'll also be talking in the last section, but the things that I'm going to be covering are talking about the fundamental concepts behind power analysis, and then James will take over talking about the decision making in power analysis and then how to actually do one in jamovi, and then I'll take over again at the end talking about ways in which you might be able to do more advanced kind of power analyses, things for like ANOVAs, regressions, and so on. So if you move on there for me, James. So like I said, I'm going to talk about the fundamental concepts behind power analysis, and that's going to kind of take two parts. So the first part is talking about the key concepts, and that's kind of one, how does null, what are we even talking about power analysis for? What's the framework that we're working within? What is power to begin with? Like, what do we mean by power? What do we mean by effect size? Like, these are all terms, key terms that you will have heard when hearing about power analysis. I'm going to clarify all of that, and then I'm going to talk about why we care about doing power analyses before handing over to James. So in terms of the background where we are, null hypothesis significance testing, or NHST, is the main way that scientists have been analyzing their results for any of their studies for the last 100 years. And this is kind of called a classical framework of statistics, and that's what we've kind of existed within for the last century. And at its heart, this assumes the null hypothesis, i.e. that there's no effect. And we then compare that against our study data. And this comparison to the null is done using inferential statistics. So the question is framed as how likely is it that data we see here deviates from the null? And the way we assess that is using something called p-values. So the p-value tells us that if the null were true, so if our assumption was correct, and we did run the experiment, but we ran the experiment an infinite number of times, what percentage of the results would be the same or more extreme as the results that we see in our current study? And if the p-value is low enough, we kind of have as accepted as a kind of psychological community, or if you're not in psychology, as a science community, that there is enough evidence to say that the null may not be fair to continue to assume. And so we reject the null in favor of an alternative hypothesis. And so I've spoken about the p-value there. And what we call the p-value is kind of the cutoff point. The p-value is the arbitrary value, the cutoff point that we use to say, okay, it's low enough that we are rejecting the null is completely arbitrary. But in general, in psychology at least, it's used as 0.05 or 5%. So if 5% of all studies, if the null hypothesis were true, would be that extreme or more extreme, then we can say with some confidence that maybe this isn't, maybe the null isn't fair to assume anymore. One can use more or less strict cutoff points, and that's going to be focus of what James is going to talk about. And this cutoff point is called the alpha value. So the larger alpha is, the more likely we are to reject the null, and the lower alpha is, the less likely we are to reject the null. So kind of a quick question for you to consider in chat, and you can feel free to write your answers. If we are less strict, what might happen? So what are some of the concerns that we might have if we're less strict with P? So if our alpha value is higher, we're less strict. Currently don't see anyone responding in chat. So, oh, here we go. We might incorrectly reject. Yeah, even when the null hypothesis is true. Yeah, so we might have a false positive. What Anna has said is that we might have the thing, and then the inverse. If we're more strict, we might have kind of the opposite to be true. So this is, by the way, the alpha value is not to be confused with alpha reliability. That's a separate concept. Kind of mathematicians like using Greek letters. Ignore that fact. Just know that alpha, when we're talking about paraanalysis, is different to reliability. So I've kind of brought on the idea of false positives. So that's when we're rejecting a null that's actually true. So as Anna pointed out in the chat, we can see that if we make our alpha less strict, we're more likely to have a false positive. So a larger alpha is more likely to have a false positive, and a smaller alpha is less likely to have a false positive. A type 2 error is a false negative. It's the other side of this coin. And this is when you're failing to reject a null that should be rejected. Or in other words, you're failing to detect the effect that's actually there. You're failing to detect a true effect. And the chance of a false negative is called beta, because alpha is false positive, and now beta is false negative. And historically, psychologists have used a kind of cutoff point, which again is arbitrary, of 20%, or beta as 0.2. And as a side note, given the difference between kind of that 5% of alpha and 20% of beta, it's kind of clear that psychologists, at least, have historically been more okay with missing something that is there than finding something that isn't there. But that isn't necessarily the case that it has to be that way. And James will go into that. But now let's talk about statistical power. So in plain English, that is the likelihood of successfully detecting an effect that's actually there, which is kind of what I said before, but there are other lay definitions that you can use. And when we say that a study is well-powered, what we're actually saying is the study is designed so that it's sensitive enough to be able to detect the effect that we think is there. And we're making the study sensitive enough to avoid type 2 errors. So that's the idea of making a study that's well-powered. And because of this thing about talking about detecting effect that's actually there, the whole point is that the power is just not doing a type 2 error. And so the way that we describe power is kind of mathematically, it's 1 minus the percentage chance of having a false negative. And therefore it's kind of 1 minus beta. So if you have a beta of 0.2, you get to 80% power. And this is a rhetorical question. What do I mean by the word effect? So I've been saying the word effect a lot lately, and kind of that can mean many things to many people. So if I go on to the next slide, in short, the effect is the difference or relationship between variables. For example, the variable of does a car have a turbocharger has an effect on top speed. So the amount of that change in top speed would be what we would call the effect size. So there is the effect, and then there's the effect size. And so in the next bit, I've given an example where adding a turbocharger to cars increased a car's top speed by an average of 30 kilometers per hour. So increased is the effect, and then 30 kilometers per hour is the size. So the size of any effect of interest is always important to consider. And I'm so sorry the builders have decided to start banging today. Measuring effects in unstandardized units like kilometers per hour is definitely one way of doing things, but it can be awkward if you're not comparing like for like situations. So for example, adding a turbocharger to a VW Golf might have a different effect. So it might give you a 10 kilometer per hour boost in top speed, but adding onto a Porsche 911 might give you a 50 kilometer per hour boost in speed. And that would average out at that 30 kilometers per hour that I've put above. But because they have a different baseline kilometer per hour, it's not necessarily fair to compare them. And so in these instances, we might use kind of based on like the average of that already known population. So if we say adding a turbocharger increases it by, X means or X standard deviations, that would be something we call a standardized effect size. And the most commonly used standardized effect size sizes in science tend to be Cohen's d, eta squared, or R. There are others, and Laken's has some great examples of where and where you might find them and how you might use them. So finally, the last kind of thing to think about when we're doing pair analysis is the sample size. So small effects are much harder to detect than large effects. And this is fairly intuitive when we think about the example I've given you here. So if you to test someone's reaction time before and then again after they've had a single shot of vodka, you might notice a very, very small change in their reaction time, but it's not really perceptible to the human eye. So you might need to study lots of participants before you can determine that there's likely an effect, especially given there's like variance in how much it affects people. So you might have someone who's less affected by, a single shot of alcohol. So their reaction time isn't affected much, but someone could be affected much more. With that variance, it's hard to detect a small effect. Whereas someone's reaction time before and after drinking a full bottle of vodka, so a full 50 centiliter bottle of vodka, is going to be very obvious. Even to the naked eye, you're going to see it. And so you might not need nearly as many participants before you can determine that there's likely to be an effect. So that's how sample size and effect size interact. So smaller effects will need more participants. And then the flip side of that is if you have more participants, you can more reliably detect smaller effects. And that is the two core principles behind the two kinds of pair analysis that we're going to be talking about today. So finally, bringing all of that together, pair analysis is kind of a way of answering one of two questions depending on the type of pair analysis we're doing. So the first question we might ask is how many participants might we need to make our study sensitive enough to detect a true effect, which is at least a certain size. So we know that there should be an effect and we think it's going to be about this size. How many participants do we need to make our study sensitive enough to actually detect that effect? And the second question is, what is the smallest effect size that we can detect in our study, given that we have a set number of participants or a set sample size? And the first of these questions is far more prominent and is kind of used or assessed using a pair analysis that you may have heard of before called a priori pair analysis. And this is one that tends to be spoken about when people talk about pair analysis in general. That's the kind of thing that they tend to be talking about just off the, without having a prefix. They tend to mean a priori pair analysis, but also they might mean, if they're answering question 2, instead they will be using a sensitivity pair analysis. And so this sensitivity pair analysis allows us to see, okay, basically this study with X many participants, how sensitive is it? What's the smallest effect size that we can measure? So finishing off this section, I'm going to talk about why we care about pair analysis. So James and I have both published talking about how to do good science and why doing good science is important. And you can read about that elsewhere. But part of doing good science is also about not wasting limited scientific resources. So researchers only have so much time to do research. There's only so much research funding that people can have both in their own projects and also distributed among different researchers. If a participant is spending time in your study, then they're not spending time in someone else's study. And there's also only so many, articles that get published a year. So when a study is overpowered, we might be wasting resources that don't give us much extra information in terms of finding a true effect. So for example, we might have someone whose study and they've got, 1,000 participants and they're already starting, they're looking for a large effect. So they know that their kind of effect is going to be fairly easy to detect. And they've got 1,000 participants, but they've got enough research funding to potentially look at another 1,000 participants. So instead of using that research funding to just collect more data in the same study, it might be better off to use that research funding to design a follow-up study or a study that is a conceptual replication, that kind of thing. So that way the research funds aren't wasted but kind of just confirm something that you've already found at that point. The converse of that is when a study is underpowered, we're less likely to find a true effect that's actually there, meaning that an interesting but expensive study might be wasted insofar as it might be that there is an effect there, but you just weren't sensitive enough to detect it because you couldn't recruit enough people because you were underpowered. And as a result, that can be a problem. And that's significant if it might, it's significant because if something is statistically significant in your results and you have an underpowered study, that might be because of chance. You don't know because that's, it could be in that 5% of results that is in the null hypothesis being looking like it's actually there. And so if something's significant, we don't know when a study's underpowered, if that's because there's actually a true effect or because it was pure chance. And conducting power analysis helps to limit those issues, both in interpretation and in resource management. So before I hand you over this final slide, I'm going to talk about when to use which. So in some research, you might have an effect in mind that you want to study, but you don't know how many participants you might need in order to recruit. And that is kind of the majority of studies in psychology and the majority of sciences, of other sciences as well. And in these instances, you would use an a priori power analysis. Whereas something that's becoming more frequent in parts of research, especially because of big data, is the use of a sensitivity power analysis. And you would do that, for example, if you were working on secondhand data. So let's say the Dutch government collected data, and then you were going to be working on that data set. So you already know how many participants were in that data set. But before you go in, you can't just root around and test 15 million effects and go, oh, this one happens to be significant, because that's kind of just, of course, something's going to be significant if you're by chance, if you're doing that. So what you want to know is what's the smallest effect size that I'm likely to find? And the same can happen with other big data science things that are kind of happening in the advent of big data. And there's also rare populations. So for example, in some of my work, I've worked on research with people with rare genetic disorders, where we haven't known, like there's only going to be maybe 300 people in the entire country who could be recruited. And so we need to know, okay, even if we manage to recruit, say, 2/3 of the entire possible population of 200 people, what kind of effects could we even actually be likely to find? It's not just, oh, well, we'll just recruit more participants because there aren't more participants. It's, okay, we know we're going to have a set maximum. What effects should we be looking for? So as well as these factors, there are other decisions to be made when conducting power analyses. And James is going to spend the next 2 sections going over what those decisions are and then showing you how to conduct a power analysis in Jamovi. And I'll now hand over to James.
Thank you. I was going to say you're a little bit ahead of time to what you timed. So does anyone have any questions about part one? So like the fundamental concepts before we move on to more of a decision making. And I do apologize if I sound a little bit funny. I've been ill for the last couple of days, so I'm sort of battling a cold. And while I give people a little bit of time to type if there are any questions, the sort of picture here is like not quite sure how old it is. I guess from a type, maybe like 50s or 60s, but like an example of like overly honest sample size justification, where I started a tweet and made me laugh, and I thought it'd be perfect to share here, where it's like had 5 normal participants, 5 obese participants, and the justification was like, yeah, we didn't recruit a lot of people because it's hard to collect data. because some other people is unreliable. So a little bit overly honest. It's unlikely you'll see things like this, but as we'll cover in theory, the key part is just explaining this justification behind the sample size. The specific reason is more down to you and what you argue. Right, if people do have questions on those concepts, happy to take them as we go along. So to structure this part, I'm going to be thinking about the 4 key concepts that Sarah's explained. So in terms of decisions, the first thing is typically you start with research question, your hypothesis, and in an ideal world, you would design a study off the back of that. So what statistical test, what data do I need in order to best address that? So that's going to be your first thing. And when we go through the examples, we'll demonstrate 2 types of statistical tests. So one if you've got conditions, one if you've got groups, but this is going to be a former key part. And then there are 4 key elements to power analysis, and there is a relationship with all 4. So if you know 3 of them, you can calculate the 4th. So alpha and power are normally the ones that stand out. And then I've put, if applicable, for effect size and sample size, as they're normally the ones people are leaving free. So they're the ones you want to calculate. So in a priori power analysis, you're saying that you have a given alpha, power, and minimum effect size. So you want to know, right, how many participants would I need to achieve that? And then sensitivity power analysis is when you leave effect size free. So you state alpha and power, you have a known effect size, and then you want to know for these other parameters, what effect size could I detect? One of the things we didn't talk about, but in our tutorial article we warn against, is sometimes you will see people calculating it for power. Sometimes this can be appropriate. A lot of the times it's not appropriate. So you might see something called post hoc power. So this is where at the end of a study, you see reviewers request this all the time because they think it's going to be really informative, where you'll say, right, for the effect size you have, for the sample size you have, what power did you have? So the idea was that, and in an ideal world, this would be a great thing to have, where if you can detect, if you can calculate the power of your experiment, it would help to know, like, okay, do we have, is it a real effect? Is it a potentially false positive? But because of the philosophy of statistics that p-values are based on, you can't get inferences about your individual sample. Remember, it's about long run frequencies. So when you work out post hoc power, all it is the p-value expressed in a different way, where if you have a significant p-value, you had enough power for that scenario. If you didn't have, if it wasn't significant, you didn't have enough power. So it's not really informative, so we're not really spending much time on it. So the first element of that is choosing alpha. So with demonstrating power analysis in section 3, in theory, it's very easy. You can plug the numbers in, and then you get the output out. But it's the actual decision making, the justification that you have for those different values that is going to be, that's going to have an effect. That's the thing that people are going to be interested in. So the first one, alpha, how many type 1 errors, how many false positives are you willing to make? So traditionally, we worked to 5% in psychology. One of the things I didn't ask on the Menti quiz at the start was what kind of disciplines people were coming from. So we're both psychologists, so we come at it from a psychology perspective. And for all these decisions, I've got some examples on the side of, so hopefully in the wild, when people have been using them for power analyses just to demonstrate these different concepts. So this is from a pre-registration for one of my studies where I included alpha as 5%. It's one I personally have the most trouble justifying, other than 5% because it's 5%. Which is what a lot of the tradition goes with. One common method is adjusting for multiple comparisons. So there have been some recent arguments about whether alpha should be lower, like the 2 citations in this screenshot, like the Benjamin et al. And the Larkins et al. So argue 2 different ways about how you can come to terms with that. Either confirmatory results should be 0.5% instead of 5%. Others, the Larkins paper was more about having a bespoke alpha, which I'll get to in a second. But one of the more common ones, particularly in neuroscience, is adjusting alpha for multiple comparisons. So having 5% as the starting point, but what we want to do is maintain like the family-wise error at 5% rather than the individual studies that can potentially be inflated. So alpha decreases. So one example of this is in this study, having it where because there was a large number of comparisons, instead of 5%, they only considered significant results at less than 0.001 to 0.1%. And then the one I genuinely couldn't find an example of is I could find lots of examples for tradition, lots of examples for adjusting for multiple comparisons, but with this sort of more contemporary approach of having like a bespoke alpha for your study, so arguing for a particular alpha value. It's the decision I have the most difficulty with. There is one article by Meyer and Larkins who offers sort of two approaches to it. So one is balancing the error rates. So they have an approach of instead of just looking at 5%, 20% for alpha and beta, how you can balance that depending on their inferential goals. So they use an example of a cost benefit analysis. So this might be easier in some areas than others. Like my research in cognitive neuroscience historically, and it would be quite difficult, at least for me, to approach it like that. But in other areas, say if you're more of an applied psychologist, it might be a little bit easier. So some people work in, say, like user interface research. You could define things on like the potential costs, the potential benefits, and include that in to decide whether you value more type 1 errors, your false positives, or whether you value false negatives. And then the second one is decreasing it as a function of sample size. So Sarah mentioned big data. And there is something called Lindley's paradox, where once you get increasingly large sample sizes, even when the null is true, p-values below alpha are more common than above alpha. So one of the approaches there is if you've got a huge sample size, you can decrease alpha to sort of counteract increasing sample size. For beta, a little bit easier, but as sort of an example of my research, again, haven't really provided justification. So CVs just as examples of how people have done it in the wild, because when I talk to students, one of the difficulties is paraanalysis is still disappointingly rare. So it can be difficult to just see what the potential is. So how it's used in research just as inspiration, how you can deal with it. So for example, this is the same screenshot for one of my studies for a pre-registration. And I put 80% power, but pretty much just based on heuristics like everyone else has. So do it as a do what I say rather than what I do kind of thing, where these are different approaches, and ideally you should be at least implicitly justifying it. Having fewer false negatives. So typically, if you're doing a paraanalysis, you're worrying about this thing. Normally it's going higher. You want to make fewer false negatives. Another one, so from a group of students I had, using 90% power instead. So we wanted fewer false negatives. This applied to regression. And then some authors argue that we should have matching error rates. So if we take 5% alpha to be the default, 5% beta should also be the default. So this is going to have an increasing number of participants. And this is actually one of my personal favorite examples of sample size justification in the wild of someone using it in an article. So they had a paraanalysis for a small to moderate effect, so correlation of 0.2, and they needed 266 participants for 95% power. A one-sided alpha of 5%. So they want matching error rates. They want neither or as few type 1 errors as type 2 errors. But one of the things we'll come on to a little bit later, and which is why it's one of my favorite examples, is they also follow that up with a sensitivity paraanalysis. So they have their final sample, but then they also consider, okay, now we have this final sample, what could we do with this? And they give like a range of, we would have a high chance of detecting effects of 0.15, and a very high chance, so higher power at 0.2. So given a range of what effects they could detect with their study. In terms of effect sizes, so this is where we're thinking about a priori power analysis, different strategies here. Label this first one as the smallest effect size of interest, but all of them are somewhat related, where there are different methods of deciding what for you is the smallest effect size of interest. So this first example is from a meta-analysis by Quintana, and he was interested in oxytocin research, and they didn't have like a theoretical reason of what would be the smallest effect for this area of research, like what would we consider interesting, what would we not consider interesting. So they set this bound based on what the meta-analysis could find. So essentially the confidence interval around what it could detect, and they use that to argue what their smallest effect size of interest would be. So any effects within that, smaller than that, closer to zero, they would consider not very interesting. Another method is looking at a previous meta-analysis. So similar to the last approach, but some people don't consider it the smallest effect size of interest, more just the meta-analysis in general. So here is an example within smoking. So they found that like when you compare smokers and non-smokers, the average effect is about 0.88, so quite a large standardized effect. But then a few things to think about is how similar these estimates are to your study, how consistent they are. So if there's a lot of heterogeneity, how that will likely impact how it applies to your study. So with this, previous studies, what I sometimes do is use like the lower bound of their estimate. So for the confidence interval here, it's 0.3. So instead of using the average effect size, so the middle value, using the lower bound to sort of combine these strategies of the smallest effect size of interest, but using it based on the evidence from a meta-analysis. So the smallest effect size that would be consistent with the evidence in this study. Similar approach if you're using just a previous study. So if it's in an area of research where there's not enough for someone to have used a meta-analysis to collate lots of studies and find the average effect, sometimes you could use the effect size from one particular study. So say if you wanted to replicate it, say if you wanted to build on it. This is also quite a nice example where it's also using this smallest effect size approach, where rather than just using the effect size that they observed, they kind of overcompensated it and almost doubled the precision they was aiming for. So in the original study, they say they had an effect of eta squared equals 0.04, so 4% of the variance. So they was looking for 90% power, and they would need 250 participants, but they wanted to overcompensate here. So you could argue like what Sarah's talking about, or whether this is potentially a little bit wasteful. It'd be nice to see a little bit stronger justification, which they do get into, about why you would want to overcompensate that much. So they ended up having 900 participants, which would have power to detect eta squared equals 0.017. So 1.7% of the variance rather than 4% of the variance. And then one thing just to have a little bit more warning around. So one really common method of deciding on effect size is through Cohen's guidelines. So the idea behind Cohen's D of 0.2, 0.5, 0.8, really common. But one, there's essentially guesses. So in Cohen's original work, they were kind of heuristics about what would be, you'd need statistics to find, what would be obvious, what you could observe with naked eye. There's pretty much Cohen just firing out suggestions. They weren't particularly precise in different areas of research, and they don't really map on to different subdisciplines very well. So Cohen's guidelines are the most commonly reported when people use meta-analyses. One of the studies in the reference list is by Bakker et al. In 2020. And what they did is like a systematic review of all the power analyses and looked at the different parameters people use. And people still use all the Cohen guidelines, but they're not a very good idea. It's better if you are going to go down this route to have subject-specific effect size distributions. So that means instead of just very generic, look for what would be useful for your study. So for example, Quintana, one of the authors talked about previously, has one specifically for heart rate variability studies. This one on the screen is about cognitive neuroscience. So instead of 0.2, 0.5, 0.8 in Cohen's guidelines, it's 0.1, 0.4, 0.75 for small, medium, and large effects. So if you use Cohen's guidelines, it's essentially been an overestimate, and you could potentially have lower power for what would be more reasonable effects for your area of research. So see if you can find something that's going to be more appropriate. And then the last thing, depending on how you're approaching this, if it's more of a sensitivity approach, there are different reasons that you can start with a known sample size. So if you're very lucky, and what seems to be always out of Sweden, if you have a whole population of interest. Sarah talks about some of her research. This might be a bit smaller. If there is, say, if you work with people with very rare genetic disorders, it's going to place a cap on who could be your participants. Not every area of research has thousands of MTurk workers, thousands of undergraduate students. It might be much more constrained. So this study had a whole sample of people who were conscripted into the Swedish military. So they had, I think, a couple of million participants, and they was looking at, I think it was stress, I think it's something to do with suicide and stress. But they had the whole sample. So they almost didn't need inferential statistics because they just had the whole population of interest. But then you can think of, when I have my sample size as a fixed number, what could I do with it? What is the possibilities? So you can see like what effect size you could detect with the sample size you have. Like the kind of tongue-in-cheek example right at the start, you could have resource constraints, absolutely valid approach. Hopefully it's a little bit more than 5 people because they're a little bit awkward. But particularly for undergraduate students, particularly for people without funding, it can just be a matter of time. So for example, here, it was undergraduate students, and we just collected as many people as we could until the end of term. So sometimes if you don't have much to go on, that can be about as precise as people have. But in the past, people would just go, okay, that's all we can do. Who cares about power? But then the reason we're emphasizing the sensitivity power analysis so much is power still applies. So you still need to know what would be reasonable. What can you do with your study? So could you meet your inferential goals based on your area of research, or is it just going to be hopeless? And then the other common approach can be secondary data analysis. So you're using data from a secondary source. So this one on the right was from one of the original Center for Open Science Replication projects. So they had 366 participants. They had access to that data. So as they kind of comes across as a little bit sassy, like the sample size was, of course, out of our control. So they had 366 participants, and they were thinking, right, with this fixed sample size, what could we do with it? So having it based on the effects that they started with or had an idea about, they would need 78 participants for 50% power for whatever reason. And then it was close to what they would need to achieve 90% power. So it's almost this combination of a priori, what would they need with what they have. And the final thing here is, these are decisions you have to make and explain to people. In theory, there's no right or wrong answer, as long as you can justify it to yourself and to the scientific community you're trying to communicate your results to. So it is about balancing your inferential goals, so what you want to achieve with this study, with the resources you have available. Because in theory, I would love to do every study 1% alpha, 1% beta. I don't want to make any errors, but you've got to explain that to a funder. You've got to be able to have the participants available to you. So you've got to be able to balance those competing interests. Particularly, so I'm like teaching focused lecturer, so all my dissertation students have very little money. It's going to be constrained by the amount of time they have, but you can still think about power as we're emphasizing as this sensitivity part. And for some of the things we'll emphasize in the demonstration part, if you're doing a priori power analysis, you're calculating how many participants you would need. this is the best place to do it, because you can make decisions that hopefully make your study more efficient, so need fewer participants, while still having an adequate level of power. But then one of the things, so talked about at the start, we've got, this is built off a tutorial article we'd wrote. One of the rare reviewer comments is like, oh no, that's a genuinely very good suggestion. Was we originally put, yeah, you probably want to avoid underpowered research, but they said like, no, there are actually some scenarios that this, you just can't get around it. And we kind of make the point at the start where underpowered research isn't a problem if publication bias didn't exist. So if it was conditioned on results being significant, all you ever see are massive large effects because they're the ones that are significant with small samples. But if it's underpowered, you'll just get lots of non-significant findings, tend to be smaller effects. So if you do research and it is underpowered, there's nothing you can do about it. All you can do, share the results, share the data if possible, not always. So in future, people could do meta-analyses, say if it's on rare genetic disorders, you could have estimates from UK, estimates from the Netherlands, estimates from Germany. Each country might have a small number of people, but if you have access to like the results of the data, combine them into a meta-analysis, hopefully be a little bit more useful. Right, they're the kind of decision-making parts. Does anyone have any questions off the back of that part? So one thing I'm going to do, so hopefully this will be interactive. So if you haven't downloaded Jamovi, one of the things I'm going to do is stop sharing my screen a moment. Because I don't want to just do a whole session running through Jamovi because that's going to be super boring. But I'm just going to sort of open it up, show how to negotiate with it if you've never used it before and you've downloaded it in prep. If you haven't downloaded it before, bear with me, I'm just getting the download link. You can download it from this website. If your internet's decent, it should be pretty quick to download. And on the slides, I will run through in a second how to get to the power analysis part. But while this opens. Oh, good question, Marcel. So something we're not covering now, because one, you can't do it in Jamovi. So our main focus here is on beginners parts. So one thing, so what would hopefully be more useful to you, I've put it in the chat, but if people haven't seen, if you follow the link I included earlier to the OSF project, we have both the slides and we have references and an annotated bibliography. In the annotated bibliography part, there's one section called what happens if like you can't collect more participants. There's this cool study by Baker et al. And they talked about it, I think it's called something about power contours. And it's specifically designed at neuroscience and talking about the one method to get around this is increasing the numbers of trials and have more precise estimates. So have a look in the annotated bibliography for an article by Baker et al. They talk about how you can consider the number of trials in a power analysis as well. And some of the others talk about simulating things for a mixed effects model, which we'll come on to later. And that can also handle trial level data. But good question. But we're not going to spend much more time on because this is very beginner focused. So hopefully if you have Jamovi on your screen, Sarah highlighted that you might have a different version. So it's a little bit older on my laptop. But it looks a little bit like this. If you've never used Jamovi before, ooh, that's a great question, Luna. I'll get back to that in a second. Yeah, if you've never used Jamovi before, it's great. Particularly if you're coming from, say, using SPSS. Not sure what software people normally use, but it's meant to compete with that. But one, it's free, so it's badass. But it also has lots of other options that you just can't do in SPSS. Because it's open source, people can add to it, which is where these modules come from that we're going to be using today. So if you open it up fresh, you've never used it before, you can enter data on the left or import data, your output comes up on the right. And where we're going to be going is, if you've not used it before, modules in the top right and Jamovi library. And what this does is bring up all the modules that are available to you. So the one we need is JPower, so it should be relatively near the top. If you've never installed it before, you get a little install button like this. Because I have it already, it's listed as installed. Once you click install, it will add to the menu at the top. And then there are different options available. There are lots of things it can do that SPSS can't do. I just like to poke fun at SPSS. And when you have it open, on the menu, so on the slides I'll come back to in a second, it will hopefully be very clear which menu item you need. And then I've blown up the output so you can hopefully follow along. Put the inputs we're looking at. I'll emphasize the outputs that you would get from that. Yeah, thank you, Sarah. So currently, you can do independent sample t-test, paired samples t-test, and a one sample t-test. So it's quite limited, quite constrained, but we like it as a kind of educational experience. As if you can understand the decision-making, the thinking behind what goes into these simple cases, you can then scale it up to the more advanced scenarios, which we'll touch on towards the end. So if you still need to download, you'll have time while I get the slides back. Right, and yeah, back to Leonor's question. So really good question if you haven't read it. So is there a point where power becomes superfluous in terms of big data sets and large groups? So not so much as a rule of thumb, but that's where that sensitivity comes in mind. So I think it's a separate problem where at the moment, and I haven't included anything on the annotated bibliography for this, but it's definitely an issue where, because people are used to working with, yeah, it's a nice problem to have. Because people are starting with, well, the kind of reference point a lot of psychology projects are, the sample sizes are typically very small, in the sort of magnitude of, say, 50 to a couple of hundred. You'll get larger examples. People love using MTurk, so you get like thousands of questionnaire samples, that sort of thing. But this is more of a personal opinion. I'm not sure what data supports it. People are almost conditioned to what to expect on these smaller samples. So with p-values, with power, it's almost like a signal detection thing where people look for the significant results. They think, okay, that is important, because in these smaller samples, the kind of bigger effects are the ones that are significant. The smaller effects aren't significant, so people don't see them as important. So p-values have almost been used as, this is important, this isn't important. When you have big data sets, everything is significant. So there's something, if anyone's ever heard of the, I guess he was a clinical psychologist, more a philosopher of science, Paul Meal. Is it Paul Meal? Something Meal. His research, his articles, there's something called Meal's paradox, where as you get an increasing sample size, it's easier to reject the null hypothesis. So when you're thinking about a theory and making clear predictions, when you have huge samples, you can have super small effect sizes, but it's still going to be significant. So it becomes redundant. And then there's also this thing called the crud factor, where it's like with increasingly large samples, you just get lots of tiny correlations that are significant, but are they actually meaningful? So it's really thinking about the effect sizes. So you could have lots of participants, but you need to think about whether, like, what effects would be meaningful in your area of your research. There is a paper published research, again, and sorry to go on a huge tangent, it's just an interesting problem. I think it was by like Gertz, and it was talking about like the beauty of like small effects. So in lots of research, small effects are going to be more important. And that sort of thing. I think there's a little bit of pushback on it, but it talked about this effect of when you have big samples, you can start to care about whether smaller effects are going to be more important as more of like an additive process, because there's lots of aspects of human behavior. It's very unlikely that you're going to have like one study showing like a Cohen's d of like 0.6. If you could do that, people would have abused it by now. So it's probably lots of additive little effects. And going back to Lorenzo, and I'll move on because I'm a sucker for losing track. What effect size could you use if your study is quite new and cannot find any previous studies examining relationships you're interested in? So in the third part of the second part, when it's talking about like different approaches to justifying your effect size, there are different options. So if it's new, typically you're relying on like those effect size distributions as similar research as possible. So it's those approaches that have slightly less precision on what effect sizes are likely in your area. And then depending on how much data there is whether you can rely on, say, one study and thinking about the uncertainty around the estimate, how close it is to the study you want to perform. With increasing numbers of studies, are there meta-analyses? But it's typically that in decreasing order of kind of precision informativeness, where it's like those subject-specific effect size distributions, individual studies, meta-analyses, thinking about what the smallest effect of interest would be in different ones like that. And Leonie, G-Power is good. So our article came from, so I wrote like a long guide about G-Power, about different software, and it kind of came from that to be a little bit more focused and user-friendly. But I've got like a longer guide that's in the bibliography where doing all these in G-Power and jamovi and showing how you can do it in both. G-Power is great. I find it horrific in terms of user experience, which is why I wrote the guide in the first place. You can do more things in jamovi, but it's also not in development. I think the last update was in 2017. It's no longer in development. So on my Mac, because it's because it no longer accepts 32-bit software, you can't use G-Power on it anymore, which is annoying. And yeah, so I liked jamovi as kind of like the user-friendly option, and then personally prefer things like R for the more advanced options where to have that more flexibility. But G-Power is still cool. If you know what you're doing, it's fine. I just find it horrific in terms of like a newcomer coming to it. Right, let me move on before I completely lose track. So to kind of recap the things already covered, hopefully you've got it downloaded from this brief interlude of me rambling. But if you haven't, there's the link in the chat. Yeah, thanks, sir. Sort of stare me on. If you need it, modules in the top right, click on jamovi library, need to scroll down under available and click install under J-Power. And you should then have a menu item called J-Power to work with. So for the first example we're going to work with, so as just mentioned, I think it's Zuck and Ioannidis. We use the effect size to be, I haven't really explained it here because it's just demonstrating how to use it. But we take the medium effect size from cognitive neuroscience. So this D equals 0.42. The first one we're starting with is an a priori power analysis for an independent samples t-test. So from the menu, you will need independent samples t-test. We want to know how many participants do we need in two groups to detect our effect of interest. So when you've opened that up, you will see the menu on the left-hand side, and this is where you put your different parameters. So for an a priori power analysis, I think it's the default, but under calculate, there are different options. And for a priori, we want n per group. So this is saying we want the number of participants as our outcome, the thing we want to know. For minimally interesting effect size, we've set it to D equals 0.42, which just mentioned from a Zuck and Ioannidis paper, is the medium effect size they found in cognitive neuroscience. Minimum desired power, aiming for 90%. Personally, I think 80% is a little bit low. 95 would be nice, but sometimes it can take too many participants. So Personally, for me, 90% is like a kind of happy medium in between. N for group 1 is grayed out because we want to know the sample size. So we're working out the N per group. So this will be blanked out because we're not entering it. You can change the relative size of group 2 to group 1. So setting at 1 means your 2 groups will be the exact same size. Changing it to below 1 will mean group 2 will be bigger than group 1, bigger than 1. Group 1 will be bigger, or the other way around. Can never work out relative ratios. Other way around. Thanks, Sarah. Alpha talked about keeping it traditional. You could argue that it should be lower. So having a 5% alpha. One thing we haven't really talked about here, more specific to t-test, so between 2 groups, 2 conditions. We can also have a two-tailed test, which is the difference could be positive, the difference could be negative. We're happy for either. Or you can change this to one-tailed, where you're going, if it's to support my hypothesis, group A must be bigger than group B. So it's normally more efficient. We'll come back to that in a second. But for two-tailed, having it like that. And plots, I think this is all by default other than maybe power contour, but make sure you click that because we'll come back to it in a second. If you have these all as inputs, it should come up with the output that you can see on the right-hand side. So detect with 90% power, an effect of D equals 0.42. You would ideally need 121 people in each group. So 242 people in total. Might sound quite a lot compared to a lot of cognitive neuroscience papers. But based on the average effect, so this isn't even the smallest effect size of interest. This is the median effect in cognitive neuroscience. This is ideally what you'd be looking out for 90% power. The other section, so it doesn't change. So it says a priori power analysis. It doesn't actually change. Just the parameter, the output you're looking for does. And then helpfully, like the Vingham paper talked about when they, as an example of changing beta or change of power, you have like this power by effect size table. So it will tell you based on the effect that you've put in, how likely would you find these. So on the next slide, show an example of a power contour. So how power isn't a fixed figure. Power exists along a curve. So by saying that you want to power for effects of 0.42 with 90% power, you would have the power you're looking for, so sufficient power for 0.42. So you can see that in the row that's like 80 to 95%. 0.42 is within that range, and we are probably going to detect that. But if the effect is bigger, so if it's bigger than 0.47, we are almost surely going to detect it with 121 people. For smaller effects, we are less likely to detect it. So between 0.25, 0.36, probably going to miss it. Smaller than 0.25, we're likely going to miss it. So this is where that reflective process is going to come in of the effects I'm interested in. Am I likely to detect it? Unlikely to detect it. Scrolling down in the output, you should have a power contour. So this shows that with larger sample sizes, you can detect smaller effects. So when I mentioned that power exists along a curve, what this shows is in the thick black line that curves round, this is set to the power you're interested in. So here it's in that boundary between kind of very light green and yellow because we want a 90% power. And if you follow that curve round, so on the y-axis, we have the effect size. So lower on the y-axis, smaller effect. To detect smaller effects, you need larger and larger sample sizes. So if you follow that curve down, say we was interested in an effect size of D equals 1, you need around 22 participants-ish. If you wanted an effect of 1.5, it would be like 7 participants. Smaller effects, so if you're following that curve down to the bottom, you're going to need more and more participants. And for our effect of 0.42, we needed 121 people. So if you're performing this power analysis in the design phase, this is what gives you the most amount of freedom. So at the end of the last section, when I talked about you can change your parameters to see how this affects how many participants you need. So this can be effective if, say, you know, a budget of, right, I can afford to collect 200 participants. So you can think about, okay, how can I design an experiment that's going to be both informative and affordable? So when you're designing a study, you can explore the parameters to see how it affects how many participants you would need. So for example, holding everything constant, so all the same inputs as before, but if you decrease alpha to 0.01, so say you wanted fewer type 1 errors, instead of 121 participants per group, you need 171. So you need more participants to make fewer type 1 errors. If you changed it to a one-tailed test, so this is changing everything back to default. So if you change alpha to 0.05 again first, holding everything constant. If you change it to a one-tailed test, this decreases the number of participants you need. Now, if you have like a very strong hypothesis and you go, right, I'm only interested in group A being bigger than group B, don't want a two-tailed test, I can test that hypothesis specifically. You save resources. So instead of 121 participants, you only need 98. So if you had a budget for 200 people, change it to one-tailed test would mean that you could be in budget and both perform an informative experiment. But again, say you turn that back to a two-tailed test and 90% power isn't good enough, you want 95% power. That, again, you need more participants for higher power. Here you would need 149 participants per group to detect an effect of 0.42. So think about this as a reflective process. Smaller alpha, so fewer type 1 errors, you're going to need more participants. One-tail test, you need fewer. More power, you need more participants. So now we're going to change it to a different scenario. So still within independent samples t-test, but instead of how many participants we would need for a given effect, we're going to think about sensitivity. So all you need to do here is change under calculate, instead of n per group, you want it as effect size. So effect size will now be the grayed out one. Because imagine we didn't do a power analysis. We just went and got 40 participants in each group. And instead of how many participants we'd need to detect an effect of interest, what effect size could we detect with our known sample size? So imagine you only had 8 participants in total, 40 in each group. What can I do with that? So keeping the other parameters roughly the same. So 90% power, we've got 40 in each group. So remember, if it's slightly different, you can change the relative size of group 2 to group 1. But we're approaching the simplest case. 5% alpha, two-tailed. With 40 per group, all we could detect is, by the Zucken Ioannidis paper, a large effect. Even for cognitive neuroscience, it's 0.73. So approaching also Cohen's a guideline for a large effect. So you would have to think, okay, based on the area of research, is that likely to be informative or not? So based on your understanding of effects in previous research, you've done the study, so there's nothing you can do about it yet, but is it going to be informative for your area of research? If it's not significant and all you had the power for was very large effects, could it be the case that an effect could be there? It's just smaller than you had power to, so you can think about whether your study was sensitive or not. And like I said, by default, again, I think it's power contour that's missing by default. So make sure you tick both of those, because then for sensitivity, you have this power curve. So it's slightly expressed slightly differently to the power contour on the last slide. But here again, power exists along a curve. That's a really important point to say. When you have that fixed point, that's the intersection of these two things. But that doesn't mean like you're setting the effect size of, you're trying to work out, is that good enough? Yes or no. So if you follow the curved line from the bottom to the top, you would have increasing amounts of power for the effect sizes. So if you want 90% power with 40 participants, when it meets the curve, you know, all you can detect is, can't remember exactly off last side, like 0.73. But you would have greater power for larger effect sizes and lower power for smaller effect sizes. So always remember, power exists along a curve. It's just when you end up with a final sample size, that's what's fixing that arrow in place. And you know, you can detect larger effects with greater power, smaller effects, you're more and more likely to miss them. Now we're going to switch to two conditions. So in the menu at the top, instead of independent samples t-test, we want paired samples t-test. Menu options are going to look very similar, but because we have two conditions, it's slightly simplified because there are less parameters to enter. So we're going to start with a priori again. So how many participants do we need for a given effect size? So make sure calculate is set to n. Notice it's not n per group because we've just got the same participants in multiple conditions. And we're going to use the same effect size. So from the Suchinidis paper, median effect size cognitive neuroscience, D equals 0.42, 90% power. N is grayed out, remember, because we want to know how many participants we need. 5% alpha, two-tailed. And now we need 62 participants. So the next important lesson for this is, if you can do it, within subjects, designs are a whole lot more efficient. So if you remember from the first example, for the same effect, we would need 242 participants in total for a between subjects experiment. But for within subjects experiment, we would need 62. So more than half the number of people. So it's not always possible if there are things like expectancy, if it's going to be quite a subtle manipulation. Some studies can't be converted to a within subjects design. But if it is, and normally what I encourage my undergraduate dissertation students to do is, if you can, within subjects designs are going to give you more bang for your buck. It's going to provide a more sensitive experiment for so 242 in total, 121 in each group, but here it's just 62 in total, so more than half. And we've also got the table at the bottom, again, thinking about the sensitivity. More likely to detect larger effects, less likely to detect smaller effects. Haven't repeated the power contours and the power curve here because it's the same for both of them. Hopefully you can just apply that understanding, just focusing on the sort of novel information you get from the paired samples version. So here you need to change calculate to effect size instead. So we're now focusing on sensitivity power analysis. So we have a fixed sample. Imagine we had our dissertation student go out, she collected 30 participants. What could we do with that? So we want 90% power, 30 participants is our fixed sample size, 5% alpha, two-tailed test. And now we know we can detect an effect size of 0.61. So we would again have to think about, is that sensitive enough? Are we likely to capture the effects that are going to be meaningful for our area of research? And that's what we can do with 30 participants. Remember, power's on a curve. If the effects happen to be bigger, we would have increasing amounts of power. If the effects were smaller, we're increasingly less likely to detect it. So to summarize the key lessons from this part, holding everything else constant, if you have an independent samples design, so 2 or more groups, you need more participants to design an informative experiment. If you want to lower alpha, so if you want to make fewer type 1 errors, you will need more participants. If you want greater power, you want fewer type 2 errors, you will need more participants. If you can do a one-tailed test. So not always possible. When you get to more complicated designs, it doesn't always work. But for these simple ones, if you can do a one-tailed test because you have a specific hypothesis you want to test, you will need fewer participants. So it's a more efficient study. And again, if you can have a within subjects design, dependent samples design, you will need fewer participants. So again, more efficient. So as a little bit of a tester, so now is the time if you want to try and apply what we've just talked about. So if you've got Jamovi open, and put your answers in the chat box. Imagine we designed a flank test. So if you've never seen it, it's like arrows either side. So 5 arrows. The arrow in the middle is either congruent, so pointing in the same direction as the outer arrows, or incongruent, pointing in the opposite direction. We want a simple experiment. Can we detect the difference between these two conditions? We collected 41 participants before the end of the semester. What effect size could we detect with 90% power and 5% alpha? So if you've got Jamovi open, think about what statistical tests we need. So think about the description, think about what type of power analysis, whether it's going to be a priori, sensitivity, and what's the outcome we're focusing on. And if anyone has any questions about stuff covered while we're between these, feel free to ask. You can have a go too if you want, Antonio. Yep, so that's the second question. So what about the first? So what effect side could we detect? Yeah, perfect, Anna. Yeah. Yeah, so with 41 participants, we could detect effect of 0.52, 0.519, depending how you round it. And this is where that context comes in. So we would need to know with a sensitivity power analysis. So there's some of the keywords I was missing out to see how you followed on what information we have available, what can we do with it. We would have to think, okay, our study can detect quite reliably, so 90% power, an effect of 0.52. But is that good enough? So this is where some of that subject knowledge will come in. So for example, there is this really cool study looking at how consistent effect sizes are for different cognitive experiments. And they found for flanker tasks, you would expect an effect of about D equals 0.65. So because we can detect an effect smaller than that, we'd be pretty confident we could detect effects that would be likely for this context. So we wouldn't be too worried missing out on effects that would be likely for this area of research. And for a second situation, imagine a slightly different study. So again, think about some of these keywords, what we wanted to the output, what type of design we're applying it to. Imagine we wanted to randomly allocate participants read disfluent information or fluent information and measure their performance via a knowledge check. So example I like running for research methods courses because it's a fun little experiment. If you make it like hard to read, do people remember more? So based on previous research, so study looking at this disfluency effect, they found an effect of D equals 0.55. What sample size would we need to detect this effect with 90% power, 5% alpha? And then we'll come on to the other question in a second. Oh, don't worry about that. No, just assume assume a t-test works. It's just like a percentage correct on a knowledge check. So all we're worrying about is the stuff we've covered today. Yes, of it. If I'm pronouncing your name correctly. Perfect. So yeah, 90% power, effect D equals 0.55, 5% alpha. We would need 71 people in each group. But sort of like the question earlier, typically when we're deciding on an effect size, we do not know the precise effect size we're expecting, because if you knew the effect size that's coming out of it, you will need to do the study because you'd already have that information. So typically, and how it combines with the idea about the smallest effect size of interest is it's both what is like the likely effect. So in this previous study, they report an effect of D equals 0.55, but based on their sample, there is uncertainty around that. So one method around this is something called the small telescopes approach. So I think that's covered in the Larkin's paper, where it's what would the study you're basing it on what effect size could it detect with 33% power? Don't ask me why 33%, I can't remember. It's just one method of deciding what would be like an underestimate of the effect size. So if you follow this, instead of 0.55, what happens if you expected a smaller effect? So try and compensate for the uncertainty around the estimate. What happens instead of 0.55? We expect an effect of 0.38. What would the sample size need to be then? So all I need to do this bit is just perfect. There we go. Just on time, Anna. Yeah, exactly. So instead of 71 per group, we would need 147 per group. So almost 300 participants to detect this smaller effect. So you'd have to decide on whether that effect is reasonable or not. How would you justify this in, say, your method section when you're writing about this to people? How did you decide on that effect? And normally what I do, and I guess come back to that other question, if I'm less certain about it, I will have this almost as as a range. So again, it's that combination of what is your inferential goal? How many resources do you have available? As projects are normally either time-bound, money-bound, I would normally say okay, I would expect an effect somewhere between 0.38 and 0.55. I'll aim to collect at least 71 per group because that would be reasonable. And then for as long as I have available, say until the end of the semester, I will collect at least 71 up to 147 per group. So it will be within that range. It might not be that you have one specific answer. It's just about explaining to people what would be a reasonable effect for your area of research. How have you justified your stopping rule for what your sample size will be? So sometimes you just cannot have a specific number. And the last thing from me for this section is, in the tutorial article, we give an example of how you can report a power analysis, but the specific format isn't important. You just need certain information to make sure it's reproducible to someone else. They can see the rationale behind it. So this is the backer article I mentioned earlier, and only 20% in their sample of I think 150 were actually reproducible. So think about the key information of what type of power analysis. So is it a priori, sensitivity? You see this wrong all the time. What type of statistical test has it been applied to? So here we're just worried about independent samples versus paired samples. What software did you use? This is important for reproducibility. So for example, here we use Jamovi. What parameters did you use? So this is our alpha, power, effect size, sample size. And ideally, why did you choose? Yeah, sorry, I missed that one off. Yeah, so if you is it one or two tailed? Sometimes that doesn't apply if you're applying to these more advanced concepts. And then why? So what's your smallest effect size of interest? What did you base it on? Did you have time constraints so you could just collect 40 participants? Could you have a set amount of money? You collected data until the end of the semester. Like the Larkin's paper, really honesty is the best policy here. Looks a bit odd, like probably don't put because people are lazy and unreliable, but just because of the resources you had available. But thanks for listening to this part. Enough rambling from me. I really need to blow my nose. You might you might hear it in my voice. But then Sarah's got the last really short part, so don't worry, it's almost over.
As James said, this next bit's going to be a fair bit shorter, just talking about where you might look or where you might find one, information, or two, kind of the means by which you can actually go ahead and do para-analysis and more advanced models. Because obviously we've shown you using Jamovi how to do t-tests, but as inbuilt into Jamovi at the moment, there's no way of doing anything more than that in terms of para-analysis. So what I'm going to talk about is basically other things. So it's already been mentioned today, but G-Power is an example of something that lets you do things with more complex models. So it has ANOVAs, it has regressions, it has various other types of tests. And there are guides out there on how to use G-Power, including the one that James has written. But what I will say is that in general, G-Power I have found can be, as someone, when I started using G-Power as a kind of a novice user, it can be a bit overwhelming knowing which parameters to fill in and how to fill them in and why you're filling them in the way that you're filling them in can be a bit confusing if you don't already know a lot about the statistics going on. So there are other websites and or other apps and softwares that you can use to do various things that can also do things that G-Power can't do. For example, PowerUp lets you do mixed effects modeling up to 3 levels. So mixed effects modeling is like regression on steroids. It's it takes the concept of regression and then says, okay, but what if we had not just, you know, is the teacher experience correlated with student performance? It's okay, is teacher experience correlated to student performance in certain school districts, right? So you have like, or like between different schools versus school districts, and you can have multiple layers built up, and that's what mixed effects models do. You can also look at web power, which is a similar idea. Superpower both exists in, and so does PowerUp, both exist in the form of Shiny apps and in the form of R packages. If you are inclined to do coding and you kind of know how to do R or Python, for example, there are packages that you can use. And I've linked, so you can see all of these things are kind of different color text and underlined. That's because all of these are linking directly to where you can find these things to go away and use them. But there's also kind of taking this to the next level, simulation. So simulation is kind of a method where you generate data kind of out of thin air using code. This is not real data. This is kind of definitely fake data. And it's fairly kind of obviously fake because it's kind of generated with pre-specified parameters. So you can say, I'm going to set kind of create 50 random kind of items that have a mean of 15 and a standard deviation of 4. And I will take a second group and I will also make that have the exact same parameters. So each of the individual points are randomly generated around those parameters, but like, you know, person one or you know, item 1 in group 1 might be different from item 2, which will be different from item 3, different from person 4, and so on. But they will around about have a mean of 15 because of this pre-specified random generation, and they will roughly have a standard deviation of 4. That won't be exactly those, it will be as close to those as a random generation can do. And then if we kind of test to see if there's a significant difference between these two groups, then that gives us one output. But if we do that again and again and again, for example, say 1,000 times, so we generate 2 groups and do a test, generate a new 2 groups and do a test, generate a new 2 groups and do a test, and so on and so on and so on. We keep doing that. And eventually what we will find is that basically we need to see how many of those tests are significant. So this is a question for you guys now in the chat. Given the above parameters, roughly how many of the 1,000 tests would we consider to be likely to be considered significant if we had an alpha level of 0.05? Yeah, so Anna said 5%. That's correct. So we would expect 5% or 50 of their tests, roughly. It might be slightly more, slightly less, because obviously the p-value assumes, or the alpha value assumes, that you're running infinite tests. But if with 1,000 tests, it will be close to 5% or close to 50 of those 1,000 tests should be significant, assuming the null hypothesis is true, which in this case, we have generated the two groups to be in line with the null hypothesis. There shouldn't be a difference between them. But even though there shouldn't be a difference, roughly 5% of them would still show a significant result. And yeah, the more simulations you do, the greater precision you'll have, as James just said. So what if we set the difference in parameters to be a specified effect size? So if we have a group one of 100 people with a mean of 0 and a standard deviation of 1, and a second group of a mean of 0.4, so the only difference is the mean, that is by definition a Cohen's d of 0.4, because that is how you define Cohen's d. It's if the standard deviation of 1 and the mean difference of kind of 0 point whatever Cohen's d is. So is 100 participants in each group sensitive enough to reliably detect it? This is not a question for you to answer. This is kind of a question that we ask ourselves when doing simulation. And so what we can do is, again, generate 1,000 such data sets where we have these two groups and run a t-test on each of them. And then we find the percentage of the significant results out of 1,000 will actually tell us the power of our study, because we know there is an effect. So now we want to know, is 100 people in each group powerful enough to detect that effect reliably? And how reliably are we detecting that effect? Well, the percentage that we do detect it, that's our reliability. So if we detect it at least 80% of the time, then we have a power of at least 80% and so on. So I just happen to know that Cohen's d with 100 participant I happen to know that that's the case. Just because that is a round number, 100 participants per group was a round number that my brain remembered like from 5 years ago, and don't ask me why, brains do weird things. Anyway, next slide there, James. So you can change the parameters to be whatever you want. So you can change the mean of group 2, you can change the standard deviation of group 2, you can change both. You could change the n for one group or both groups. You could even generate more data in this way. So kind of have an extra group or an extra variable. And this is how you can run more complicated models. So doing an ANOVA, for example. So if you had, instead of 2 groups, if you had 3 groups, that would be effectively doing a one-way ANOVA. And as long as you know how to analyze data using a coding language, which, an ANOVA test is fairly simple in R, for example, then you can probably simulate data and simulate a power analysis to do it. Because all you have to do is basically say, here is how I'm going to create a data set. And the next slide will tell you how you can do that, or guides on how you can do that. And then you just run a test like you normally would if you had the real data from your real study. So yes. So Vit asks if there's no true effect, p-value should be uniformly distributed, and the answer is yes. So this here is kind of various ways that you can use, or like R packages or guides that have been created for people to run simulations for power analysis. And the reason this is really, really useful is basically, if you can code it in terms of the analysis side of things, you can probably code the simulation of it. So if you are experienced with R or Python or some other kind of coding language, basically, if you know how to code the analysis, you probably know how to code the simulation. It's just about knowing how to generate data sets. And so the guide by Julian Quant on power analysis by data simulation blog series, he says a guide basically for everyone. The part 1 is a really, really basic idea of how do you even generate a group with a specified parameters, and then provides an example of a one sample t-test being basically flipping a coin and the power analysis of how do we know if it's, on a rich coin, basically. So one sample t-test, we know it should be a set number of 50% either way, and flipping it And if it doesn't go to that, then you can kind of see, is it conforming to that 50%? If not, that's a one sample t-test. And he kind of goes over doing that. In part 2, he talks about other t-tests. So the ones that we've gone over today in Jamovi, he talks about how you can do those in R. And then in part 3, he talks about a 2x2 ANOVA. So now we're talking about the kind of models that you might be more likely to see in a psychology article or a study at master's or PhD level. So the things that you guys here today might be interested in. And then in part 4, which was released in September of 2021, so only a few months ago, he put part 4 up talking about mixed effects models. And this is the one I was talking about where you have multiple level things. And mixed effects models can also include longitudinal analysis as well. So you can see that there's lots of resources out there. Now that you've got the basics, you understand what power is, we've given you the basic concepts, and we know you shouldn't be too afraid on how to apply those concepts now. So that when you run into those concepts in these guides, which often start, they don't necessarily assume the base level, they assume, okay, you know what power is, go from there. We now have given you that base level knowledge of this is what power is, now you can use these. So I think that's everything that I had lined up. And so today, feel free to ask us questions over the next kind of 10-15 minutes. After which, if you have more questions, just send us an email, either James or to me. I've only just started a role at Coventry University again, so I've got 2 email addresses at the moment, but I will be looking at both. So if you do send me an email, feel free to just send us one, and we'll answer any questions you have. And I believe James has posted the link multiple times throughout today's talk, but we have a link to these slides and to the annotated bibliography, which is basically just saying, here is an article and this is why we think it's relevant, and you might find that useful as well. So thank you.
Thank you. I'm also going to pause to stop the recording so people can feel more free maybe to ask the question. As mentioned also in the beginning, our vision and aim is to provide you with information, support, and with a space to explore and apply open science practices. We will keep on posting recordings from our events, and hopefully in the future with more content focusing on your questions relating to open science research. It would be of great help if you would subscribe to our account and press the bell so that you can be receiving a notification whenever we upload a new video. Until then, see you soon.